The universe is 13.8 billion years old. Humanity has existed for roughly 300,000 years. We've had rockets for less than a century. And in that time, we've done something remarkable. We've sent spacecraft past every planet in our solar system, landed rovers on Mars, and even pushed a probe past the edge of the sun's influence into interstellar space. And yet, here's the part nobody tells you. Even at our fastest speeds, using our best technology, it would take that same probe over 70,000 years to reach the nearest star, not the nearest galaxy, the nearest star. We are not just far from the rest of the universe. We are locked inside a cosmic prison cell so vast that even light, the fastest thing in existence, takes over 4 years just to reach our closest neighbor. And the deeper you dig into why that is, the more you realize this isn't just an inconvenience of distance. It's something closer to a fundamental law written into the fabric of reality itself, quietly making sure we stay right where we are. Tonight, we're going to find out exactly why we're trapped here. And the answer is far stranger and far more unsettling than space is big. Let's start with just how big actually is, because most people vastly underestimate it. If you shrank the sun down to the size of a basketball, Earth would be a grain of sand orbiting about 26 meters away. Neptune, the outermost planet, would be nearly a kilometer from that basketball. And on that same scale, the nearest star system to our own Alpha Centauri wouldn't be down the street or across town. It would be roughly 7,000 kilometers away, farther than flying from New York to London and back. That's the scale we're dealing with. Our entire solar system, with all 8 planets, every moon, every asteroid belt, it's a tiny bubble of activity floating in an ocean of nothing. And nothing is doing a lot of heavy lifting in that sentence. Because between here and the next star system, there is functionally empty space for trillions upon trillions of kilometers. No fuel stations, no rest stops, no shortcuts. Just cold, dark, radiation-soaked vacuum for longer than the human mind can really comprehend. So the first reason we're trapped here is almost embarrassingly simple. The distances involved are not just large, they're absurd. They break our intuition the same way trying to imagine $1 trillion breaks it. We say the words. We don't actually feel the scale. But distance alone isn't the real prison. The real prison is what happens when you try to cross that distance, because that's where physics starts getting genuinely unsettling. Here's the fact that changes everything. Nothing with mass can travel at the speed of light. Not theoretically someday, with better engineering. Not, we haven't figured it out yet. According to Einstein's theory of special relativity, one of the most rigorously tested theories in the history of science, as an object with mass accelerates closer, and closer to light speed, its effective mass increases, and the energy required to keep accelerating it climbs toward infinity. Let that sink in. To push a spacecraft to the speed of light, you would need an infinite amount of energy. Not a lot. Not more than we currently have access to. Infinite. There isn't a fuel, a reactor, or an engine design in any near-future roadmap that gets around that. It's not an engineering problem waiting for a clever solution. It's a hard ceiling baked into the geometry of space-time itself. So even in our wildest, most optimistic science fiction fantasies, we're not talking about zipping to another star system in a few hours. We're talking, at best, about approaching some meaningful fraction of light speed, say 10 or 20%, and even that would require propulsion technology so far beyond anything we currently possess that it borders on fantasy. And even then, the math is brutal. At 20% the speed of light, a number far beyond our current capability. Using engines that don't fully exist yet, even on paper, the trip to Alpha Centauri would still take over 20 years, one way, for the nearest star. Now expand that outward. The Milky Way galaxy alone is about 100,000 light-years across. Even traveling at the speed of light itself, which, again, is physically impossible for anything with mass crossing our own galaxy, would take 100,000 years. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. We're not just trapped in our solar system. At these speeds, we're trapped in our own cosmic backyard, staring out at a universe that might as well be sealed behind glass. But here's where the story takes a genuinely eerie turn, because it's not only about speed, it's about time itself starting to work against us the moment we try to leave. Special relativity doesn't just cap our maximum speed. It also describes something called time dilation, the strange, thoroughly proven phenomenon where time itself passes differently depending on how fast you're moving relative to something else. The faster you travel, the slower time moves for you relative to someone who stayed behind. This isn't speculation. It's been measured directly, using atomic clocks flown on airplanes and satellites, confirming Einstein's predictions to a stunning degree of accuracy. GPS satellites orbiting Earth right now have to correct for time dilation every single day, or your phone's location would be wrong within minutes. Now imagine applying that effect to interstellar travel. If we ever did build a ship capable of reaching a significant fraction of light speed, the astronauts on board would experience time slower than the people back on Earth. A journey that feels like a handful of years to the crew could correspond to decades, or even centuries, back home. Which means even in the best case, wildly optimistic scenario where humanity solves the energy problem and builds a genuinely fast ship, the people who leave Earth to explore the stars would return, if they returned at all, to a world unrecognizable. Everyone they knew, gone. The culture, the technology, the entire context of the world they left, reshaped by the sheer passage of time back home, even while their own journey felt comparatively short. It's a one-way ticket disguised as a round trip. And it's not because we lack the courage to go, it's because the universe has built time itself into the price of admission. If that doesn't unsettle you a little, let's go one layer deeper, because even if you ignore the propulsion problem and the time dilation problem, your body itself becomes the next obstacle. Human beings evolved over millions of years on a very specific planet, with a very specific gravity, a very specific atmosphere, and a very specific magnetic field shielding us from deadly radiation. The moment you leave that protective bubble, your body starts fighting a war it wasn't built for. In microgravity, astronauts lose bone density and muscle mass at an alarming rate. Even with hours of mandatory daily exercise, astronauts on extended missions can lose significant percentages of bone mineral density in just a few months. Now imagine years or decades in deep space rather than months in low Earth orbit. Then there's radiation. Earth's magnetic field and atmosphere absorb the vast majority of harmful cosmic radiation before it ever reaches us on the surface. Step outside that shield, into interstellar space, and you're exposed to a relentless stream of high-energy particles, some originating from our own sun, others from exploding stars, and violent events clear across the galaxy. Extended exposure raises serious risks of cancer, damage to the central nervous system, and long-term degenerative effects that current spacecraft shielding technology can only partially mitigate. In other words, even if we solve the physics, even if we build the engine, the human body itself might not survive the journey intact. We are, in a very real sense, biologically engineered to stay close to home. So distance keeps us here. Physics keeps us here. Our own bodies keep us here. But there's a fourth reason, quieter, more philosophical, but arguably the most unsettling of all, and it involves a question that has haunted physicists for over 70 years. It's called the Fermi paradox, named after physicist Enrico Fermi, who reportedly posed a deceptively simple question during a lunchtime conversation with colleagues. If the universe is so vast and so old, and so full of stars similar to our own sun, then where is everybody? Think about the math. Our galaxy alone contains an estimated 100 to 400 billion stars, many of which we now know host their own planetary systems. The universe is 13.8 billion years old, more than enough time, in theory, for at least some civilizations to have emerged, developed technology, and begun exploring or signaling their existence across the stars. And yet, despite decades of searching, despite pointing radio telescopes at the sky, scanning for signals, watching for anomalies, we have found nothing. No confirmed contact, no unambiguous signal, just silence, stretching in every direction across a universe that should, statistically, be teeming with activity. There are dozens of proposed explanations for this silence, and it's important to be honest about which ones are grounded in evidence and which ones remain speculative. Some scientists suggest that intelligent life is simply rarer than we assume, that the specific conditions required for complex life to emerge are far more delicate and improbable than we appreciate. Others propose that civilizations do emerge regularly, but tend to destroy themselves through war, environmental collapse, or unforeseen technological risks before they ever develop the capability for interstellar communication or travel. This is often called the Great Filter Hypothesis, and it comes with a genuinely chilling implication. If the Great Filter lies in our past, we got lucky. If it lies in our future, we may be walking toward it right now. And then, there's a more speculative, more unsettling category of explanations ideas that remain firmly in the realm of hypothesis, not established science, but which continue to circulate seriously in academic and scientific discussions. Some researchers have proposed what's sometimes called the dark forest hypothesis. The idea that the universe is silent not because life is rare, but because advanced civilizations have learned that broadcasting your existence is dangerous, and the safest strategy in a universe of unknown threats is to stay quiet, stay hidden, and avoid drawing attention. Under this framework, the silence isn't emptiness, it's caution, or worse, it's what's left after someone else's mistake. To be clear, this remains speculative and unproven a thought experiment as much as a scientific theory. But its persistence in serious scientific conversation tells you something about how genuinely puzzling the silence really is. Whatever the true explanation turns out to be, the practical result is the same. We are, as far as we currently know, profoundly alone, separated not just by unimaginable distances, but by a universe that, for reasons we don't fully understand, has given us no confirmed evidence of company. So let's bring this all together. Because when you stack these reasons on top of each other, something genuinely unsettling starts to emerge. We're trapped by distance so vast, our minds can't truly picture it. We're trapped by a hard physical speed limit woven into the geometry of the universe itself, one that no amount of future engineering can simply outsmart. We're trapped by time itself, which warps and stretches the moment we try to move fast enough to escape, quietly ensuring that leaving means never fully coming home. We're trapped by our own biology, shaped over millions of years for one specific planet, ill-suited for the radiation and gravitational starvation of deep space. And we're trapped in what appears, so far, to be a profound and unexplained silence, a universe that should be loud with other voices, and instead gives us nothing back. It's tempting to feel small in the face of all that, even a little hopeless. But here's where the story shifts, because there's another way to look at every one of these barriers. Our solar system, this prison we're describing, is also an extraordinarily rare and precious pocket of stability. A star that has burned steadily for over 4.5 billion years, providing just the right amount of energy in just the right range to allow liquid water and complex chemistry to flourish on at least one small planet. A planet shielded by a magnetic field, protected by a thick atmosphere, positioned at just the right distance to avoid being a frozen wasteland or a scorched husk. The same distances that keep us isolated also keep us safe, insulated from the more violent, chaotic regions of the galaxy, buffered by unimaginable gulfs of empty space from whatever dangers, natural or otherwise, might exist out there. In a strange way, our cosmic isolation might be less of a prison and more of a shelter, a quiet corner of the universe where a species could emerge, evolve, and eventually ask questions like the ones we're asking tonight, without immediate interference. And, crucially, none of these barriers are necessarily permanent. Our understanding of physics is still evolving. Concepts like generation ships, capable of sustaining human life across multi-century journeys, remain firmly theoretical, but they're being seriously studied. More exotic ideas, wormholes, theoretical shortcuts predicted by the mathematics of general relativity, or the Alcubierre drive concept, a theoretical method of warping spacetime itself rather than moving through it conventionally, remain deeply speculative, requiring forms of exotic matter and energy we have never observed and may not even exist. But the fact that serious physicists are exploring these ideas at all tells you the walls of this prison, while currently unbreakable, aren't necessarily written in permanent ink. We've only had the technological capability to leave our own planet for less than 70 years. 66 years ago, we hadn't even reached orbit. Now we have robotic spacecraft operating past the edge of our solar system, sending back data from farther away than any human-made object has ever traveled. If that kind of progress is possible in less than a single human lifetime, it's worth asking, with genuine humility, what might be possible in the next 500 years, or the next 5,000. So here's the truth we're left with tonight. We are, by every measurable standard, trapped. Trapped by distance, by the speed of light, by time dilation, by our own fragile biology, and by a universe that has, so far, chosen not to answer us back. But being trapped isn't the same as being finished. Every barrier we've talked about tonight is a barrier as we understand physics today, not necessarily a barrier as physics will be understood a century or a millennium from now. The same species that once believed the sun orbited the Earth eventually built a telescope capable of photographing galaxies from the dawn of time. The same species that once thought flight was impossible put footprints on another world within a single lifetime. Maybe the silence out there isn't a wall, maybe it's a waiting room, and maybe the deeply unsettling answer to why we're trapped in our own solar system isn't really about limitation at all. Maybe it's about timing. Maybe the universe isn't keeping us out. Maybe it's simply waiting to see if we're patient enough and clever enough and careful enough with ourselves to earn the door being opened at all.